Thanks for coming around. I just saw this really interesting talk about cancer, using artificial intelligence for cancer detection. This talk we're going to be talking about the equally noble cause of using artificial intelligence to determine if people are going to buy something or what they're going to buy next. And we're going to be doing so by using recurrent neural networks, which is a special type of neural network. The protocol requires that I speak about myself a little bit here. I've been building e-commerce sites for most of the last 10 years. About You, Rebel, Home24 is mostly e-commerce stuff. I had a break in between. I was working for 2 years at a company called Performance Advertising. They are in, surprise, online advertising. And during that phase there, we were working with this RNN, with the recurrent neural network. And like most of the stuff that we're talking here and going to be talking about here was developed at Performance Advertising. My current employer is Swarovski. Swarovski is a very large corporate from Austria, and they're currently building a tech hub here in Hamburg for e-commerce and BI, so I'm doing both of my things at the time. We're also hiring, so if you're interested, speak to me after the talk. It's a really cool employer. And yeah, let's start. First of all, before we dive into the RNNs, the recurrent networks, I want to talk about machine learning in general a little bit. So what's machine learning on a very abstract basic level is you have a set of data and you feed that data into a machine. Okay, it's not really a machine, it's an algorithm, but you just feed it into it and you expect that this thing learns about your data. And then once it's learned it, you say you have trained it, then you can pass it different data to it and it should answer your questions. Very abstract, very high level. So what could that look like? Let's have a look at this kind of stuff here. This is some cars I made up. It's totally random data. Don't pin me down on the car metrics here. It doesn't mean anything really. So what you got two different input types. You got the average mileage of that car and you got the top speed of the car. And yeah, this would be the input data. Normally, of course, you would have way more dimensions. So you would have the weight of the car, the color of the car, the number of doors, whatever. I mean, you could imagine there's like hundreds of dimensions here. Problem is, humans have a really hard time imagining something in 100 dimensions, so I'm gonna stick to 2 dimensions here. Just rest assured that the math behind is the same. If it's a 2 dimensions or 100 dimensions, it doesn't matter. So, for example, the first thing we're gonna be building could be a linear regression. I wanna build a recommendation system. I wanna train a model so that I can pass in the average mileage of a car. That would be the thing, oops, it works down here. And I'm expecting that the model would give me back what would be the top speed of that car. Straightforward. I mean, for humans, this is very easy to see. One thing which is important about machine learning is that I want my model to generalize. So I want that when I give it new data and it hasn't seen the data yet, it still gives me valid responses. So for example, if I were to give it, say, I have a car and it has an average mileage of 8, then I'd say, yeah, the top speed is probably going to be 180 or so. So you can see the point, it shouldn't break if it sees data it hadn't seen before. So how would I do this? I mean, obviously there's a connection between those dots here. It's very easy to see. It's a line going from here to here. Easy. But in 100 dimensions, this line isn't so easy to see anymore. So you need some computer power and some algorithms to fix that for you. You could start by drawing a line here. Let's say I have a line, and this line represents my model. So if I ask the model what's going to be the output at 10, it's going to give me 100 kilometers an hour. Now, obviously, it's clear to see that my model is not very good. It's wrong. And it's wrong in 2 things. It's very easy to see. One thing is that the offset, and let's call it bias for now, is too low. It should be a little bit higher. And the other thing we see is that the angle, the gradient, is also not correct. It should be a little bit higher. Yeah, so these are the 2 things. And how most machine learning algorithms work is that they're trying to find the best possible gradient, the best possible line that connects these dots. A good line now would be this. Yeah, this is a good matching line. And yeah, it probably is going to haunt you from school a little bit, but you probably remember this formula here, linear equations and all that stuff. You had it at school, I'm pretty sure you did. And what this means in the end, that there's 2 things determining what the line looks like. The first thing here is the beta 0, which is the offset, the bias. And the second thing you got here is the beta 1, which is the angle, the gradient of my line. And so you can see pretty clearly that if I want my model to predict correctly, I need to find the correct weights. So when I got the weights correct, like I do in the purple line, then my model is going to give me the best possible response. Now how that works in machine learning in the end is that you start off with some random weights here, like for example the green line, this is random weights, and then you calculate the loss. So you figure, okay, what is my line, how far is it away from the actual results? So like this here, this is the distance. And then from this loss, you can gather what went wrong about my line. So these algorithms are able to determine, is the gradient more wrong or is the bias more wrong? So they tweak it a little bit, they pipe in the numbers, they pipe in the dots you got again, do the same calculation again, readjust the weights more, and after pushing data through it a couple of times, you should be able to have the perfect or the best possible weights. Pushing in the data is called the forward phase, and then fixing the weights on the way back is called backpropagation. That's how this works. Yeah, that's a linear regression. That's quite straightforward, I guess. I could do something different now. So for example, now I want to build a recommender, and the thing should tell me, or it should give me back a response, yes, you should buy a car, or no, you should not buy that car, and that response is based on, I want a car that consumes less than 10 liters per 100 kilometer. That would be the response. So yeah, you see the green line, these would be the cars that match this criteria. One thing to note about though, that the y-axis in this case, so the green line does not represent the speed, but it represents yes or no. So if it's on the top, it's a yes, and if it's at the bottom, it's a no, it's a 1 and a 0. And so these kind of questions would be very easy to answer with an algorithm called decision tree, but since we're talking about neural networks now, we're gonna try and make our lives a little bit more difficult. And that is, we're going to be trying to find a formula that can answer that question for us. And that formula, it will look something like this. Should also look familiar to you from maths. You got this Euler's constant there. And what these functions, and let's call them activation functions, have in common is that they stay at 0 very long, and then there's this phase where they switch over to 1. So they do this curve. And again, you're going to be finding these weights. You got the beta 1, you got the beta 2. In this case, what it does is the beta 1 defines the bias, the offset, and the beta 1 defines the angle or the gradient of that curve. So if I find the right weights here, then asking this model the question will tell me, yes, buy that car, or no, don't buy that car. What you note, though, is that it's not going to be a hard yes, no. So there's this phase up here and down here. So if I'm going towards the 10 liters, the answer would be something like, you should 80% buy this car. So there's this line where it goes from 1 to 0 or the opposite. So it's not a precise answer anymore. It's like a percentage of how likely you should be buying this car. This thing comes to a limit where now we'll be looking at 2 dimensions again. I want to build a recommender and it should give me cars which consume less than 10 liters. And also the car should not drive any faster than 200 kilometers per hour. You can see here, it's going to be hard to fit our line because this thing, the blue line, we don't have, but at the moment we would get it. So it would give us a wrong result. And we could try and change the angle of the curve a little bit here, but then we would be catching that red dot here. So it's hard. It's probably very hard to fit one line that meets all our criteria. And so the problem you have at hand here, it's called the linear separability of these 2 items. You're going to have trouble finding a line that divides these two results into 2. And the solution, if you think about it, might be, couldn't we just try and to use 2 of those, like 2 lines, and make that line up here have a little dent and sort of be excluded so it gets there. And that is, in a sense, the idea behind neural networks. So let's quickly jump in and have a look at how a neuron looks like. So a neural network is made of neurons. And in a mathematical way, it looks like this. You got this neuron. To this neuron, you got the inputs. So these here, the inputs. In our case, you would have 2. So that would be the speed of the top speed of the car, and that would be the mileage of the car. Then we got those weights again. You already know them. And what you do with those inputs, you sum them up. So that's the transfer function. It's just a fancy word for it. And then at the very end, you do the logistic regression thing, where you have an activation function, where you sum up everything that comes into your neuron. And if the inputs become strong enough, depending on the input values and also depending on the weights, then your neuron fires. And this is sort of the analogy people found to how the brain works. In the brain, you got the same thing. You got the neurons and you got the synapses. and synapses drive or feed input to the neuron, and at some point the neuron fires, and that's how the brain, or like a brain cell, works at a very basic level. The previous example, how this would look like in a neural network, and a very simple one in this case. So we got our two input neurons. The input neurons don't do much, so they take in the input data, so the speed and the mileage here again. And then you get the hidden layer, it's called. And this hidden layer, again, consists of 4 neurons. And sort of what's interesting, and then the last thing is you got the output layer. What's interesting to see is that, for example, the output layer, it does not receive the input data anymore, but it receives the output of the previous layer. The white lines here, again, are weights. So think of it, it's like the more complicated version to the linear regression we had before, is if I find the right weights, then this thing's going to give me the right answer. What is the right answer? Again, I'm piping in the data, and at the very end, I have a thing where I train the model. So I'm going to say, yes, this should be included, or no, this should be not included in my response. So this is how I'm training the network, piping in the data, labeling the data as right or wrong. If the network gets it wrong, I'm backpropagating the weights and fixing the weights, saying, yeah, tweak this weight here, a little bit here, tweak this one, tweak that one. And after a couple of runs, hundreds, thousands, depends on the problem, you should have the right weights, and then your model will answer correctly. So, yeah, in this case, our network was going to have 17 weights, so the ones connecting this one here. And then each of those neurons has another internal weight, which is the bias, which we saw before, and also the output layer has a bias. The input neurons behave a bit different. They don't have the weights and biases. They just take in the inputs and feed them to the next layers. A lot of stuff. There was a crash course in machine learning. We made it through it. So in order to sort of relax everybody a little bit, I thought I'd do a little experiment of thought. Just close your eyes and imagine you just started a new job and you're just sitting on your computer happily, and your boss comes running in and he's telling you, look, I've got this book here, and I need you to figure out which of those sentences plays in winter, which doesn't. Clearly your boss is insane, but the question would be, is that doable? Can we build something like that? So if you were to go about this and do the research, you'd say, yeah, it might be possible to do, but we need some data. We need to think about how we want to process this. And so let's start with some examples. These are sentences. And in the sentences, the idea is the network should figure out if a sentence plays in winter or not. Now, the problem with language is that it's not so straightforward to understand. So you could say, yeah, let's check what words are in the sentence. So, first sentence, for example, it has snow in it, but it doesn't play in winter because the snow had melted. So the melted sort of back references the snow and changes the meaning of it. Second sentence has icy in it, which is a sort of wintry term, you could say, and it does seem to play in the winter. Also this one and this one. So you see, language is pretty hard to understand and figure out the meaning for it. So for a network to learn, I have to give it some training data, and that would mean that you give it sentences which are labeled. So these are the labels to the sentences. Yes, it plays in winter. No, it doesn't play in winter. Okay, that's a start. Problem, of course, now is that a neural network does have no idea about sentences and words and whatever. It doesn't understand anything about that. It can only deal with numbers, with integer number, like the float values that I'm passing in. So the next step, what I'm going to be doing is I'm going to take the sentence, and I'm going to take all sentences and give number to the words. I could take a dictionary and start at A, give it 1, and then AN or AB, whatever is the second word. So I just count the words, every word gets a number. And the same word gets the same number, of course, again. So that sentence would turn into something like this. Okay, fair enough. Thing here is, though, that the numbers have no meaning. So you would have red and you would have green, which obviously are semantically related, but they would have really different numbers because they're far apart in the alphabet. So it's hard for the network to work with these numbers. And then the next step you'd be doing to work with this is called an embedding. So you'd say, yeah, let's do a two-dimensional embedding, and we're going to take the words which have a similar semantics, put them in one corner there, and put those in the other corner, and so you arrange the words so they have, so you cluster them by meaning in the end, what this is. What's a bit weird about this concept, and I must admit I find it a bit hard to understand myself, is that this embedding and this moving the words around is a part of the training. So your model learns where these words should be put by itself. So by the same thing, again, adjusting the weights, moving the words about. So this stuff will come out as a part of the training, like these word embeddings. So after that, your sentence looks like this. So as I said, we project this into a two-dimensional space. So yeah, you got a vector, like tuples of 2. It's like each of them is an input vector, and congratulations, you've successfully converted your sentence into a series of numbers. Now, let's have a look at the RNN. This is where it starts now. The RNN consists of a number of cells, and you feed those cells with words, or with the vector representation of that word. In our case, our RNN consists of 4 cells, so that means the network can remember 4 words. Yeah? So, first cell gets the "d", second cell gets the snow, third the hat, fourth the "it melted". Okay, fair enough. And also you're gonna find these white arrows again. The white arrows again are weights. Gonna be talking about that in detail in a minute. And what you train your network against? Well, clearly it's the yes, it plays in winter, or no, it does not play in winter. As you can see, we're also marking the word through it. So for example, we started at the spring had fallen, and this is like the rest of the sentence. I'm taking the sentence and piping it through, and now I'm looking at the last 4 words of the sentence. And at the very end of that, I'm going to be seeing, yes, this is winter or not. And again, is this the right answer? Is it the wrong answer? Yes, it's right, or yeah, no, it's wrong. Fix the weights, back propagate the error a little bit, and then take the next sentence. So it's a lot of computations you're doing here. Inside one of the RNNs, it's going to be looking like this. So you got the input values. Oh, sorry, I forgot to mention one thing. What's important, like the most important thing about the RNN, sorry. So you not only feed the word into a cell, but also you feed the output of the previous cell into it. And that is what I meant before with the language thing, that you say the not, for example, changes the meaning of the word that comes behind it. And this is something that these networks can capture. So they can look at the previous words here and sort of transform that information at the current word. And this is why the cell is receiving the actual word it's working on, but plus the state of the previous cell. And this is how a cell looks like. So you can see the prior state is the 4 neurons here, or the 4 input values here. And the current input is the 3 input values we got here. The internal state of my network is 4 neurons, so these are these. And then again, these 4 neurons get passed into the next neuron, etc., etc. And if I'm done with it, so at the very end, then I'm going to be using the output of that thing. So that's what I'm optimizing against. And again, these black lines here, these are weights. And this is what the network tweaks around and tries to find the best combination. In real life, this kind of thing would not work really well. The problem what these networks have is that they forget too fast. So they have a problem remembering things that were said or that were in the sentence too long before. It's called the vanishing gradient problem. So they cannot remember a not that was, say, 3 or 4 words before the current word. And so they were not really good at it. They've been around since the 80s, and only in the 90s there were some newer developments like the gated recurrent unit and the long short-term memory cell, which make this internal working of a cell much more complicated. So you have a forget gate, and they can pick what information they want to keep and can pick what they're going to throw away. But conceptually, it's the same thing. You get internal state, and you pass it on to the downstream of your sentence, what comes on. Now, of course, you might rightly ask yourself, what on the earth does this have to do with customer predictions? It doesn't anything. But the reason why I chose this introduction is that I really always wanted to invent a language of my own. Because, as you saw, we used English language now. But the thing is, it doesn't need to have to be any real language. I can just invent my own language, and the language I came up with is this. And clearly, if you work in e-commerce, you're going to see this is a user journey. Here, this guy, like one user, he's going to the homepage, he's looking at some trousers, at least he wants to buy some shorts. He puts the product into a basket and checks another product, and then he goes to the checkout. And what would be the aim of my network? What do I want to learn? It's this. Did the guy buy or not? So essentially what my network is learning is he's looking at the words that make up a user session, and the output is, did the user buy or not? So the network is essentially learning, this is the thing users do when they buy. And yeah, that's what we're training against a network against. At Performance Advertising, we're using this technology. for 2 case studies that we're doing. One of them was for a really large German hardware store, like a Baumarkt. They had quite a fair number of visitors a day. They had a huge assortment. I think it was over 100,000 products, so it's like a very proper large e-commerce site. And the other thing we're trying it against was a specialty shop for kitchen machines, like some kitchen cooker machines, the small ones you get. Didn't see too many visitors, and it wasn't so much of a shop, it was more like a funnel site. You come in, you get to pick between 5 machines, and then enter credit card, enter your shipping address. It was like 4 or 5 steps, and at the end of it, you should be buying that machine. So it was a really strong sales funnel. And these were the 2 sites we had. And in order to work with it, we needed to gather the data first, of course. At Performance Advertising, we had about 8 terabytes worth of tracking data that was combined for a whole network. So first step in order is you need to go through this 8 terabytes and sift out the data for these 2 sites we're looking at. So the hardware store and the kitchen store. So yeah, then you got the data out. Next thing, of course, you got to do is you got to group it by user ID, because we don't, by cookie ID, sorry, we don't get the user ID, we did not get any user data, we only get a session hash, which is the cookie hash. And so this you use to group, and you're sort of collecting everything. You need to clean the data very thoroughly, because quite often it is broken and it's, I don't know, there's some encoding errors and it's not working correctly. So there's lots of things that go wrong with the data. And also we kicked out sessions which had less than 3 hits, because we thought, okay, this is not really meaningful because the guy didn't do too much on its side. Technology here uses Apache Spark. I mean, it's the standard, I guess, in the industry. And then once we got the data out, we're starting the training, so the model learning and weights tweaking part. That was working on 180 days of traffic. It was about 2.4 million sessions here. We were doing this for 250 times, so these 2.4 million sessions were sent through the network 250 times. In total, the network we trained for had about 200,000 weights, so you can imagine this is not possible to do by humans anymore. You need like really brutally raw operating and number crunching power here. The training took 20 hours, and the biggest problem we came across, which makes the training really hard, is the data set imbalance. Because on a normal e-commerce site, the conversion rate is between 1 to 3%. So 99% of the sessions you're seeing are not converting. So the network is really having a hard time figuring out what makes a converting session, like a session that buys, special. So what's unique about it? So that makes it hard for the network to learn. These babies here, they are really helpful. This is a Tesla GPU. They come with, 4,800 CPU cores these days, and they can crunch tons of data. I mean, they're really fast and powerful with these kinds of computations that you need here. We tried this training, which took 10, 20 hours on those, on a normal MacBook or whatever it was, and that would have taken a couple of weeks. So it's not feasible to do it on anything else. Once we got the model trained and we got the weights correctly set up, we stored this model and then we used it to predict it. So what we did is we were loading sessions that were active in the last 30 days. We filtered out the sessions that bought something already, because we thought that would sort of skew the output a little bit. And then we're sending the session against the trained model, and at the very end, the model would output, yeah, this user is likely to buy, or no, this user is not likely to buy, with a sort of possibility or like a range on how certain the model would be. This thing is really fast. It took about 10 minutes. And then the last open question, of course, is how good did it work? Unfortunately, it's actually not so easy to evaluate the metrics of such a system. What you got here is like as a binary classifier, as a yes or no. And this is what can be the outcome of such a thing. So it can it can identify a conversion correctly, that would be a true positive. And it can identify a non-conversion correctly as non-conversion, so that's a true negative, makes sense. And then it could get it wrong either way. So either it gets it says, yes, this guy's gonna buy something, but he did not buy something. So that's the thing that can go wrong with binary classification. And out of this, there's 3 metrics that come out of it. First metrics that you see quite often is the accuracy. It's like how many true and false predictions were correct. So how many did it get right? Problem in our case was, unfortunately, that the accuracy is 99% out of the box. Probably can imagine why, because of the data imbalance. So if the network just predicts everything as, no, he's not going to buy, it's going to get 99% of the sessions correct. But that's not what we want, of course. So accuracy doesn't really help you. What's more helpful is the precision. And that is, out of all the true predictions that it gives me, how many did it get right? Makes sense. Thing now, though, is that if my network only gives me one true prediction, and this one's correct, I get a precision of 100%. Even though in my data set there's 10,000 of true positives which it did not get correct. So precision is also not the full picture. Another thing is the recall. That is, out of all the existing true positives in my data set, how many were identified correctly? So that's the recall. And last thing you have is the threshold. And that is, as I said, it's not a yes-no answer. And it basically means at what point do we take a yes as a yes? So is it at 50% reliability, at 50%, or is it at 80%? So you can pick at what point of activation of that last output node you're going to take that as a yes. And yeah, this is sort of the intro to these diagrams. It looks a bit scary. But what this means is that at the bottom you're going to find the threshold. So at what point do I take a yes as a yes? And you say if I do the threshold really, really high, say like the network must be super, super sure that this is the correct answer, then of course the precision goes really high because it's only going to get one true prediction, and this might be correct, so the precision is good. But the recall, how many did it get, goes down to 0 because it doesn't get anything anymore. So the sweet spot of that whole thing here now is at about 35. So I'm getting 35% of the true positives correct, and I'm identifying out of the existing positives 35%. Now, I'm aware that this doesn't sound like much, but if you think about, if you just were to pick at random, the precision or the sweet spot would be at 0.1, because that's the conversion rate, if you just choose a random number. So 35 is pretty good, it's not so bad. It worked much better even for the kitchen machines, where you got something like this. So about 50% were correct and 50% were pulled out of the whole data set. So that's a pretty good result, and it makes sense because what the network in the end learned was the further people go into the sales funnel, the more likely they are to buy. Okay, it's probably quite straightforward, but it took a lot of computing power to get to that result. Last thing now, just very quickly on this, sorry, it's a bit not so good to see. This line here is the click-through rate, and we segmented, and the lower line is the segment. So we took the output of the network and we segmented the users. We said the lower 20% is segment 1, so we're pretty sure they're not going to buy, and the upper segment here is we are fairly sure these people will buy. So this was where the network has the highest activation on the output layer. So the numbers you see here, the lower line is the click-through rate, so of people who saw an ad, how many click on it. And that gives us an increase of about 20%. So it's 20% more people click on it based on the segment they're in. And what's really cool about is this one here, it's the conversion rate. So how many people actually bought. And that is 100% improvement. So this is 0.12% bought, and this is 0.26%. So it works. It's very clear that it works. And these numbers are comparable to if some campaign manager would be sitting there and optimizing these campaigns by hand. So this is like the automated process. Since we're a bit running out of time, one last thing I wanted to show you because I thought it was funny. And you can tweak this network and can run it differently. So in our case, what we did first is we said, okay, the output or what we're training against is yes, he bought, or no, he did not buy. What you can also do is that you train the network on what's going to be the next word in that sentence. So you see, here I'm passing in the, and I'm expecting snow to be the next word. And I'm passing snow, and I'm expecting had the next word to be. So this is a different setup. And you could use this thing now to predict what the user's going to do next. So, hey, he's on this page, which is the next page he's probably going to do. And you could use this, for example, that you say, this guy's probably going to go to the basket or to the checkout soon. I might want to give him a discount, or I might want to give him a voucher, or something like that. So that would work. We did not invest too much time in that thing, because that wasn't our use case, but we did play around with it a little bit, and that's what I wanted to show you. We trained such a network on jokes. And that's the output on it, so please beware. This is computer-generated or AI-generated jokes. Yeah, okay, they're not so funny, I gotta admit. The last one is sort of okay, I think. It would pass as a joke. But yeah, the network was trained on jokes, and it's sort of, you start with one word, and then the network gives the prediction on what it thinks is going to be the next word in a sentence, and this is where you get. All right, to wrap it up, the RNNs we were using in this case really did work, and they can give you really powerful insights on what users are doing on your site, and especially if you're thinking about the amount of data, these 8 terabytes. I mean, this is something that is beyond any human understanding and comprehension for if you want to work with this. You need a lot of data to train them, as you saw. It's quite time consuming, and also you need the data quality must be good, so a lot of effort must be put into getting this right. The output was really well, so we at the thing and sort of was competing against hand-optimized campaign, and it was sort of performing on par or a little bit above the hand-optimized campaigns. And the last thing, and that is sort of a bit of a word of warning if you want to try such a thing, from having a prototype running in a Jupyter notebook to having this running in production every 2 hours, reliable in case of failures with automatic recovery, etc., this takes about 80% of time for building such a system. It's where the most work goes into making this stable and sturdy. That was it. Thank you very much for your attention. Open for questions now.
I saw the TensorFlow logo in one of your slides. Is that what you used to train your model?
Yeah, forget to mention that. Yes, TensorFlow.
Yeah.
It's so everywhere. It's used so everywhere that I forgot to mention it. No, but I know there's other stuff too.
Okay. All right.
Did you just implement a POC, or is it going to go live someday?
It's live. They're using it in production. Yes.
Okay, so the 20-80% was what you figure out by getting it live.
Yeah, exactly. So that was the work needed to make this stable enough so they can use it. I think they're offering it as an add-on feature to their customers, saying like, hey, we can offer you this package, and it's like this machine learning, computer-generated campaigns.
Cool.
Whoa.
Sorry.
Great throw. So thank you for the introduction. I have one question. Did you benchmark it against a simpler model, like something like logistic regression with some classic information retrieval text transformations? Because you don't need a neural network to get from text or words to vectors. So
the words are not so much the thing, it's the sequence of the words, I think. So that's where the juice is. Because think about it, somebody comes to the website, and what I didn't mention, for example, in the word embeddings that we're training, we also added the times between the impressions. So for example, somebody goes to a page and adds 3 products into the basket within 3 minutes. The assumption would be that this is a strong indicator that this guy's going to buy something soon. But this is something you cannot capture with any linear regression or logistic or even neural networks, because that's sort of the temporal dimension that RNNs can grasp and other algorithms cannot.
Did you reverse the model and look into the features? Because it could be only the count of the products you added, which doesn't need to be. I mean, did you look into the model and really see, oh, I see it's the sequence of the events, or it's maybe just the event count, which would have been captured by a word model?
Interesting thought, yeah. But no, we did not do that. So.
Okay, and one second question is, this production system, is it real-time inference or is it a batch?
No, it's batch.
Okay.
Yeah. So we take the sessions, we tag them in the clusters, in the segments, and these segments are then pushed to our DSP. And the DSP then, what we did with it is with online marketing, you set bids on users. And we set the bids for the users we think gonna buy really high, and lower to the ones that we think would not buy. And so you can tweak the amount of money you want to invest in people that should see the ad.
Okay, thank you. Anyone else?
You just mentioned one part where, for example, if someone buys something or puts something in a shopping box really quickly, indicator that they might be buying. Does that mean you also included technical data into your model itself, so not just the movement, which products did they look at, how often did they go to the search page, etc., but also things like web performance, which browsers were they using, what kind of connections might they be having, because all those are indicators of whether it takes longer or not.
It's an interesting question. We had similar approaches previous to that, where we were trying to figure out sort of the conversion rate based on the browser, internet speed, etc. But the performance was the output was not really good. I don't think it really makes an impact if people are using Safari or Chrome. It might make one if you got hundreds and millions of users, then yes, but the amount of data we had is still limited. So I think it's sort of, it goes missing in the noise, so you can't really see that.
Okay, thank you.
Thank you for the talk. You have mentioned in the evaluation phase, you have filtered out all the conversions. So how did you evaluate the model if you don't know who converted in the end?
There are two evaluations. One evaluation is the model, and there I don't filter out. But what you saw with the filtering is the predictions, the inference. Because there we're still getting the data, we're not training the model, but we're throwing it again. And so, because if you put that in there, it might skew the output, because you're counting things double then. The guy has converted already, and we're counting him, hey, he converted, but so we wanted to exclude that, so it's like a fresh slate.
Okay, thank you.
Crazy technology. Can you tell us something about the network architecture in the end you used? So, like, how deep it was, and did you use LSTMs or groups, or?
Yeah, well, it was LSTMs, yeah. We had a, so we're using Keras. It wasn't super sophisticated. I mean, it was just Keras. Keras gives you LSTMs off the box. We had a sequence length of 150. Keras is configured in a way that the internal state is equal to the length you give it, so it's 150 neurons per cell. We had an embedding of, what is it, I think 8 dimensions or something, the word embeddings, because there weren't so many words. There were like 3,000-4,000 pages we were tracking, so it wasn't too many. And what else did we have? That's as much as I can remember was about the figures. All right, thank you for your questions.